So we switch over to Hokkaido.
Very interesting. Oh,
So Mr. Toyohara, can you tell us something about the biomechanic studies using finite element and 3D printed SI joint models? I will stop sharing the screen. Please take over. Yes, great. Thank you.
Okay, thank you very much. Yeah. Let's start my talk. My name is Ryota Toyohara from Hokkaido University in Japan. Yeah. And today, the title is biomechanical study using finite element and the 3D printed SIG model. This is given by this title given by the present Dr. Kurosawa. And first, I will introduce myself. Now I'm an assistant professor in this laboratory. And from the when I was a university student, I started study with Dr. Kurosawa and Dr. Niels Hammer at the Medical University of Graz. Before just before the COVID-19 pandemic, I went to his university to experience a dissertation with him. And throughout my research topic on the SIJ sacral joint, and then from last year I became an assistant professor, and in the last year I got the Yamaguchi Medal Award in the Asian Pacific Conference on Biomechanics. Yes, let's start my talk about sacral joint. So firstly, I want to show the very introduction, and as you know, where the sacral joint is located at the sacrum between the sacrum and the ilium. And the mechanical function is a shock absorber and transmitter, as mentioned by Dr. Kurosawa. And the sacral joint dysfunction may caused by the unexpected impact or repeated force, and joint state become misalignment and instability state. For the treatment option, the severe option, but the pelvic bed and joint fixation is a famous option. And I show the three components, but these come from the mechanical environment. So mechanical environment is very strongly related to the sacral joint. For that, I using a finite model and a 3D printed model I used for this study. At first, the finite model is for the visualization of the stress distribution dynamic environment. In this time, I show the working state. And the second one is a 3D printed model. This is a articular surface of the sacral joint and printed by the 3D printer. And this model for the physical experiment for the characteristics on the articular surface. So firstly, I want to talk about finite model. So as you know, the sacral joint is supported by tough ligaments, so the range of the motion is less than 1 millimeter. So that's why the X-ray imaging and the outside the observation from the outside the body, we cannot see any motion. So this means no method to observe the stage motion. So that's why we use the numerical analysis using a finite model. So here I adopted the fundamental motion on human as a fundamental motion on human is bipedal walking. In this walking, the sacral joint loading changes according to the walking paces. Here we divide it into the 5 paces, from phase 1 to 5. The phase 1 means a heel contact, and the phase 2 a singlet support on the only right knee. In phase 3, the opposite heel contact, and phase 4 and 5 single leg support. And So here, in this study, the objective is to determine the dynamic load transition on support joint during normal working. Now I show our finite models of human pelvis. The bone component and cartilage component exists in this model, and the ligament as a spring component. And here we want to clarify the role of the support joint. So in this time, we want to show what happens in case of the ossified pelvis. So for this question, we change the material property for the support joint. So we prepared the two models. First one is the cartilage model. This means the support joint, the property of this joint is cartilage. This means this pelvis with a support joint structure. And the other model is a bone model. Here, the support joint is set as a bone. This means without support joint. And then next, we apply the working loading. The working load, as I mentioned, is divided into 5 phases. And then the other boundary conditions I show here. Nextly, I want to show the result from the I will show the result. The displacement of support joint as shown here. Here is the right side and the left side. From here, we can see that on the stance phase, the displacement on the 0.6 millimeter, but the swinging phase on 0.3 millimeter. And on the pelvis, and the pelvis displacement on the cartilage model, this means with a support joint, here is a highly displacement. But on the bone model, the displacement was decreased. This is a 57% of decrease. So next, we move on to the equivalent stress. So here is a kind of load on the support joint. As we can see, on the bone model, this means without the pelvic support joint structure, this stress increased to the 380%, so very dramatically increased. Okay. But on the other hand, ligament loading on the right side, this means on the bone model, the decrease to the 23%. I will discuss of this result, how a mechanical function and importance of the support joint. On the bone model, the only bones are loaded for the working, so equivalent stress as the load increase at the support joint. So stress concentrate only on a specific part. So pelvis behave like a single bond without a joint structure. On the other hand, the cartilage model, the surrounding ligament exert power by the deformation of the pelvic limb. The burden, the stress burden, doesn't concentrate on the some part on the support joint. So pelvis can be easily deformed. The summary of this, a support joint area tend to concentrate the large stress as a structure of the pelvic limb. And support joint has a role of absorbing mechanism during bipedal walking with small joint motion. Here, I will not talk in detail, but I work on the treatment method on using the finite model. Here is a pelvic model, a pelvic belt, and the joint fixation. The both results shows a support joint motion is decreased. So this treatment can fix the support joint. So let's move on to the next topic about the 3D printed model. So in this topic, I focus on the joint surface morphology. So this is a surface joint surface on the cadaver. This is on ilium side and sacrum side. So as you know, this surface very very uneven, so very roughness, they have roughness. So, but the previous researcher, maybe not many researchers work on this biomechanics on this joint surface. So being able to show the particle surfaces are fully formed on the after 20 years old. But after once completed the model, the surface, the particle surface area and shape did not correlate with change with age. So maybe the particle surface will not change with aging. But on the circular joint dysfunction, the sacrum rotated 2 degrees on nutation. And on the biomechanical study, the investigator also investigates the static friction with the experiment. He shows that undulation areas they have a high static friction. But only these papers show the biomechanics. So here I want to clarify how the morphological characteristics of the sacral joint affects the joint motion. So in this study, I mimic the stress environment of the sacral joint. So this joint is supported by the tough ligament. So this environment applies and gives a compressive and shearing stress environment. So I'm in my test environment I mimic this stress environment. And for this experiment I prepared the surface model created by the X-ray CT imaging data. So the 3 of them is from healthy joint, and other side of three model come from the painful joint. This is a computer model come from the CT data and printed out with a 3D printer and changed to the resin model to increase the stiffness. So and then we put on the sacrum side onto the ilium side and apply the force and record the displacement. This is a testing environment. Here is a surface model, and I apply the springs for the compression, and the force gauge applies shearing force to the surface model, and the camera records the displacement. In this experiment, I measure I calculate the shear resistance coefficient. So here I apply the shear force, and then record the displacement. When the displacement was 0.5 millimeter, I get the shear force, and then I calculate shear resistance coefficient. And shear directions on sacrum is a 4 direction: superior, inferior, anterior, and posterior. And I change the rotational motion. I apply the rotational motion, the flexion, extension. This means the nutation and the counter nutation. Here is the result of the shear resistance coefficient. The high coefficient, the high number indicates that difficult to move on this direction. Here is the inferior direction shows a high resistance. In this type, the inferior direction, so this means to prevent the joint from sliding in standing. On the other hand, in superior direction shows a low coefficient. In low resistance, this means the support efficient swing during walking. This means when we walk with the legs in the right, in this case, right leg ilium become a lower size. So in this case, with a low resistance means efficient legs. And I show the rotated rotated state. In this case, in this result, we can see the resistance changes on different levels. And next, I compared on the healthy and painful joint. Here we can see that all directions, the resistance decreased on painful joint, painful side. And we I tested on the rotated position. The resistance is different, but on the previous slide, I showed the higher resistance is better on the inferior direction, and the lower resistance is good for the superior direction. So in such a in that perspective, when we see the frictional state, the result becomes the result on painful joint becomes the good better trend. So when I compare the motions resistance, what happens? This is come from the articular surface morphology. So I analyze the morphology. The left side means a sacral morphology. On the top side is a healthy joint, and the bottom side is painful joint. The red area shows the convex, and the blue one is the concave area. So we can see that this is a similar distribution. But and then we move on to the gap distance. This means the gaps on the sacrum and the ilium, between the sacrum and the ilium. From here you can see on the painful joint, the almost a blue. This means the all area means that mostly the same distance. So this means that smooth on the painful joint. And on the flexion and extension state, the here is a blue, so now, but here is a green, so a bit high, bit wider. So this means that they have a undulation on flexion and extension, so that they can get each other and fix the joint. So the discussion, articular surface on painful joint, the smooth contact between the bone, so reduce the sliding resistance. And on flexion mode and the extension, the rough contact similar to the healthy joint. So improves this means this improves the joint mobility. So adjusting the combination of the joint may be applied to the treatment. The summary of this study: the frictional resistance of sacral joints changes depending on the shared direction and the alignment position. The sacral joint surface morphology may be designed to accommodate upright bipolar walking. And finally, adjusting the combination of the joint may be applied to the treatment. So finally, I want to show the acknowledgement and for researchers. This is my lab member. He's my professor, Professor Toshiro Hashi. Yeah, here is me. Yeah, thank you for your attention. That's all.
Thank you very much for this very good talk about the biomechanics, seen from the 3D printed model and the finite element side. I think we can have 2 or 3 questions if anybody has a question about these last 2 talks. And then we will have a break of 5 minutes. So are there any questions to these 2 guys, to Dr. Kurosawa and Mr. Toyohara?
I have a question, John Stark.
John, go ahead.
How does the SPECT scan contribute compared with the changes we see on MRI, like modic changes, or the changes you see on CT scan, which is the sclerotic changes?
Thank you for your questions. So, compared to usually the patient with sacral joint pain that don't show the abnormality in MRI. In my series of SPECT CTs, they didn't show the abnormality in MRI, and some patients have a sclerotic change, but SPECT CT scan can detect the abnormality without sclerotic change in patients with severe sacral joint pain. So some patients have sclerotic change. That is not when the sclerotic change is not active. The SPECT CT cannot detect the place. There are no accumulation in the non-active area. I'm sorry, I cannot explain well.
So the SPECT scan shows active changes?
Yes, active, yes, you are right.
I see. Okay, well, thank you.
Any other question?
A question for Daisuke.
Yes.
When you had some videos of you manipulating the SI joint in a cadaver.
Oh, yes.
Do you think that during a physical exam that we have that ability to move the SI joint that much? It was pretty impressive how you were able to manipulate that without sectioning. So what are your thoughts about the physical exam and that amount of manipulation?
Yeah, so actually, I am a practitioner of manual therapy for 10 years, but I couldn't feel the movement. In the dissection, I have already cut the joint capsule and the surrounding ligament, so I can control the joint. But as you know, so in our clinical practice, we are not able to find the movement by manual hand like that.
May I ask a question following Woody's question?
Yes.
Is it necessary to move it, or are you just trying to create pain through joint reaction force?
So do you mean in clinical practice? So
But in
your question is?
I never thought I was moving the joint during my
Mm.
physical exam very much, but I am able to provoke pain, and that is the useful sign that I'm looking for. But I never thought that this pain is resulting from abnormal movement, even though I'm sure there is some abnormal movement.
Yes, I agree with your opinion. It is enough to stimulate the joint, not moving the articular region, stimulate the joint capsula and surrounding ligament.
Okay, thank you.
I see.
And just to add to your statement, John, I think, looking at Dr. Toyohara's talk and the subtle motions of shearing and nutation force, I'm wondering if we do manipulate it, this 0.5 millimeters, and that's maybe responsible for some of the pain.